Modern navigation operates on a scale that is difficult to visualize. Google Maps processes over 20 petabytes of geocoded data, utilizing Gemini AI to predict traffic patterns for more than 1 billion monthly users. This map is built by capturing the physical world in high resolution. It draws from satellite imagery, crowdsourced GPS signals from smartphones, and specialized vehicles equipped with 360-degree camera arrays. The platform has even learned to account for specific infrastructure needs, such as mapping wheelchair-accessible transit routes and identifying entrances where automated ramps are required. But despite this massive intelligence, the system's primary directive remains unchanged. It is an efficiency engine designed to find the single fastest path from point A to point B. This focus on speed creates a dangerous algorithmic blind spot. Because the software prioritizes cars and clocks, it leaves a gap in how it protects the actual person moving through the environment. For light two-wheelers, this is often illegal. Without a specific vehicle class profile, navigation apps frequently route scooter and moped riders onto high-speed motorways designed only for cars. Pedestrians face a different set of risks. The algorithm cannot see transient human dangers, like active crime scenes, civil unrest, or unlit hazardous alleys, because those variables aren't factored into the time to destination. By ignoring real-time threat data to save a few minutes of travel, current navigation tools prioritize efficiency over the physical safety of their users. Fakhar Mushtaq developed the SafePath Navigator to address this gap. It functions as an AI safety layer, designed to integrate real-time hazard data directly into the map's routing logic. Managing the chaos of real-world threats requires a decentralized approach. Instead of a single, rigid program, SafePath utilizes a multi-agent system to process hundreds of changing variables at once. Built on the Google Agent Development Kit, the system creates an environment where specialized AI agents can collaborate independently, each focusing on one specific part of the safety problem. By delegating tasks across this network, the system analyzes threats and calculates safe detours in the background without interrupting the core navigation performance. The network uses 3 primary roles. Agent 1 is for threat detection. It monitors crime APIs, social media for unrest, and emergency broadcasts to identify potential hazards. It classifies incoming alerts by severity. Detecting a high-risk event, like an active protest on the user's path, triggers a critical network flag. Agent 2, the route optimizer, responds immediately. Taking threat coordinates from Agent 1, it recalculates a path avoiding the hazard entirely. It also applies demographic weights. For a solo female traveler at night, a 2.5 times safety multiplier lengthens the route to bypass even medium-risk areas. While the user is moving, Agent 3, the family liaison, monitors their GPS progress against the new safe route. This agent manages a 3-tier escalation protocol. It texts family upon deviation, calls on a missed check-in, and alerts 911 if unresponsive. The agent-to-agent protocol, or A2A, is the nervous system connecting them. It allows these 3 AI entities to communicate and act in real time, executing the entire safety cycle with no manual input from the traveler. For the traveler, this complexity is hidden behind a simple choice. When a threat is detected, a pop-up suggests a detour based on a calculated safety score, letting the user choose protection over speed. This interaction contrasts with the standard navigation experience, where we often follow a blue line blindly just to shave a few seconds off a commute. Every time a user accepts a SafePath detour, the algorithm successfully manages a risk that traditional efficiency-based mapping would have ignored. Digital maps were originally electronic versions of paper directories, a more convenient way to find an address or business hours. SafePath indicates that AI is shifting away from that role as a passive calculator. By integrating demographic weighting and emergency escalation, these systems are becoming proactive, context-aware guardians. As these agentic networks grow, the tools we use to navigate the physical world will finally prioritize the person traveling over the speed of the trip.